Swayam Prabha. Digital India. Educated India.
Hello and welcome back to this lecture series on foundations of cyber physical systems. So, we will just start right over from where we left off. So, in the last lecture we have been discussing about this EDF algorithm, and we showed that well it is optimal among all such dynamic priority algorithms. However, we also said that well some of these algorithms do not these algorithms that we have discussed till now, they do not support this kind of precedence relations among tasks. So, let us see what kind of algorithms can be used to actually execute tasks which have this kind of precedence constraints. And we will start with one which is known as latest deadline first, or LDF. So, if we can just look at these slides, LDF is an algorithm which is optimal with respect to precedence relations, and what essentially it does is you are given a task graph. A task graph is kind of well, you have the nodes as the tasks, and the edges, forward going edges, they are actually capturing the precedence constants, that which task must execute, and after that which task can execute, something like that. So, an LDF algorithm will analyze such a graph and it will construct the schedule backward. It will first choose the last tasks, the tasks that are the leaf nodes of such a tree, we will see that. And the reason why it is done like that is that the last task does not really have anybody dependent on it. So, let us say you have a task graph like this, that only after what this graph says is only after T1 executes, I can execute T2 and T3, and T2 and T3 do not have any dependency. And let us say after both T2 and T3 executes, I can execute T4. So, this kind of constants are taken as input by this LDF algorithm, and it will construct the schedule backwards, which again means that it will first try to compute what should be the start time of this task T4. It does not have anybody who is going to depend on T4, right. So, it will just figure out the start time of the independent task, which is right at the leaf node or at the end, and then it will construct backward. It will analyze tasks which are kind of predecessors of T4 like T2 and T3, and then it will again analyze and figure out what should be the start time of task, which is the precedence, which is the predecessor of T2 and T3. So, that is how it works. Now, in this variant we are not supporting arrival of tasks, and we will soon see that well how that support can also be brought in. So, when we modify LDF with this support for arrival of tasks, that is what we call as EDF with precedences or EDF star. So, this is the algorithm which handles precedences, arrival of tasks, and minimizes the maximum lateness. So, that means at any point of time given a set of tasks, including the ones which have arrived, you figure out which task to execute, okay, and again you recompute that upon arrival of new tasks to your task set. So, that is how it works. So, what it does is it will recompute the relative deadline of the tasks. So, you have a set of tasks which are pending to execute, and some of them have arrived now, some of them may have arrived a bit earlier. So, what you have done, what you are doing is you are recomputing the deadlines of the tasks with respect to their precedence constants. So, suppose right now your set of tasks is T. So, for a task to execute, let us say task I will execute, okay. Let D I be the set of task executions that immediately depend on I in the precedence graph. So, that means once task I executes, the D I of these tasks can execute. Okay. So, what we are saying is we will recompute the deadline. That means, whatever is given to you, let us say that well this task must execute inside this time, is not really the true deadline, because if I just schedule the task based on its deadline, any task which is going to depend on this task it can only execute once this guy has finished, right. and that may be quite late for those dependent tasks to satisfy their own absolute deadlines. We will see what it means. First, let us just look at this symbolic equation, and soon with an example we will see that well how such a symbolic relation can be computed. So, what we are saying is, suppose let us say this is your task I and di is containing two tasks j and k, right, and you have somehow computed that exactly when j and k must start, right, and we want to see that well what should be the modified deadline of the task I. What do I mean is, I have already computed this modified deadlines of j and k. Okay. So, that is more like a relation here we are trying to develop between these modified deadlines of I, j and k. Suppose these are known, right. So, with respect to these modified deadlines, that means the deadlines inside which j really must execute. So, dj let us say is the original deadline of task j, but we are saying that this modified deadline is indicating the time inside which j must really execute, so that anything downstream after j which depends on j will have enough time to execute and satisfy their own deadline. So, suppose these downstream activities we have already figured, let us assume that. So, now with that being figured out, this modified deadline for j is dj prime, similarly for k is dk prime, and we want to compute this di prime, that when really I must finish its execution. So, the way to do it is, well, if this is its real deadline, then it must start at some time which is dj prime minus ej, and similarly dk prime minus ek, right. So, among these two values, which one is the minimum, that we will figure out, okay. Because if we can figure out that among these two values, which one I mean among these two values, this deadline minus execution time, if we can figure that thing out, that tells me that well that much time must be with respect to dj prime, I can leave out ej and I can say that that is the deadline of I, or with respect to dk prime, I can leave out an ek amount of time and I can see that well the rest of whatever remains that is the real deadline of I. Okay. So, I compute those differences and see who among them is minimum, right. So, whichever is smaller is going to be now compared with the real deadline of this ith task, that is another minimization, and that will tell me that well that is when this ith task must finish its execution, because after that let us say it happens to be the case that dk prime is smaller, right. I mean dk prime minus ek is smaller, that means and let us say that value is even smaller than di, that means for di prime will be equal to dk prime minus ek. So, let us say at this point this ith task will actually finish, that means I am just leaving enough time to finish dk inside its deadline dk prime, got it. So, that is how we compute this modified deadlines, and we do it from the leaf nodes of the tree backward in this precedence graph. Okay. So, essentially once these deadlines are computed, the rest of it is just EDF. So, what we are doing is we are reevaluating the deadlines by satisfying the precedence constraints of the graph, and then based on the deadlines whichever is earlier we will dispatch to the processor, and that is how we will work it out here. So, if you see here we have taken one example. So, you have this values that are given. Okay. So, you have a precedence constraint graph. So, d1 is some 2, d2 for this one is 5. This is also the example has been taken from the same book that we have been talking about in this course. That is a kind of our reference test do at least up to this much of coverage we have done. And d3 the deadline for node 3 is 4. Similarly, deadline for node 6 is 6. I mean suppose these are given, but mind that these are the actual deadlines, right. So, if we just now try and work out the relative deadlines backward. So, these are the leaf nodes here. So, their deadlines will remain same, right. So, D4 will be 3, D5 will be 5, D6 will be 6, no problem with that. Okay. What about D2 and D3? Let us figure that out. So, let us pick up this D2 here, I mean, and try to see what should be its modified value. So, if we apply, we will just apply this relation, just note it once again. So, for 2 we have 2 successors 4 and 5, right. So, you are going to compare here with D2 and then you are going to do a mean over that is it, right, and D4 prime equal to D4 equal to 3, D5 prime equal to D5 equal to 5, right. So, D2 is 5, so that makes this one to be 2, and similarly if we just do this for D3 prime, value of D3 is 4, it has got only one successor which is D6, right. So, that means you do not need this minima here. So, it is just a 6 D6 minus E6, right. By the way, all the executions times here E, those values are 1. So, that will come out as 4. Okay. So, then this 6 will get to be 4. Okay. So, now you have this set will deadlines D1 and D2 both as 2, and so not D6, this is D3 prime, right, which remains to be 4. So, that's there is no much change here, because also anyway it does not hurt because D6 is 6. So, there is quite a lot of time, 6 minus 1 5. So, whatever was it, I mean, that remains, but here you can see this guy the deadline has changed significantly. One can even say that this example is kind of built to highlight this issue, because somehow we have kept this high and kept the deadline of the later nodes to be smaller, at least this one. The idea is we are trying to show that how this guy is forcing the actual runtime deadline of these to change. Okay. So, even in your precedence constraint graph, if there is some issue like some intermediate node has a higher deadline, it will automatically get pushed to the left by nodes later on if they have a smaller deadline. So, that is kind of what we are trying to show here. And then if you just apply this EDF star or LDF, in this case it is only for a single graph, no new task is arriving. So, LDF and EDF stars are same. So, which tasks are really going to execute? So, task 1 will definitely execute, right. I mean, then after this task 1, of course, when a task executes, its precedence order has to be satisfied by the schedule, right. So, 1 executes and after that 2 and 3 both of them are free to execute. Now, if I have taken this LDF, what would have I mean, if I have taken LDF or EDF star, what is happening is this D2's recomputed deadline is 2 and D3's recomputed deadline is 4. So, it will schedule D2, right. So, that is why you see, of course, LDF and EDF star, like I said, has to be same. So, it takes the second task, and after the second task, which task to take? Well, now you see, once the second task is taken out of the equation, once this second task is taken out of the, this is done, this is done. Now, once this is done, you have a set of 3 possible tasks to execute. So, this is like your scheduling frontier now. This is done. So, these 2 tasks are free, and the initial node is done. So, this task is also free, right. And among them you have deadlines like 3, and this is 5, and this is 4, right. So, which one you execute? So, you will execute like 4 here, right. So, because that has the deadline 3, right. So, you execute the node 4, node 4 has deadline 3, node 5 deadline 5, node 3 deadline 4. So, smallest deadline value is 3, right, for node 4. So, that is what will come. So, once this is done, you have now 5 and 3 node numbers with with deadlines 5, and for 3 it is 4, right. So, 3 will come, right. So, once this is done, and now your scheduling frontier will also include this guy, but then again node 5 has deadline 5 and 6 has deadline 6. So, 5 will go and then 6 will come. Had this been EDF, had there been would there have been any change? Yes, of course. So, what would have happened is, if it is EDF, none of this recomputation would have ever happened, right. So, it would have taken D1, right. Precedence constant will force that, well, 1 has to be executed. Then after that, these 2 guys are free, no recomputation of deadline. So, this is 4 and this is 5. So, node 3 will go in instead of node 2, and then well, after that you have, so node 3 has gone in, and then you will have node 2, right. So, and after node 2, you would have executed 4, because I mean after this you would have executed node 2, you would have executed 4, then 5 and 6. Okay. So, that is how EDF would have done it. So, that is about executing and I mean executing tasks with precedences in a deadline efficient manner. Now, we have discussed rate monotonic, we have discussed this new algorithm, that is EDF star, and just for you to study, there is another algorithm called deadline monotonic algorithm. So, you can just take this as a take home exercise and study about this. We will also try to give you some problems around all these algorithms when we do the tutorials. So, that is about some real time scheduling algorithms, and the next thing that we will be discussing now is some amount of timing analysis of such multitask scheduling on processors. So, we are calling this topic as processor level worst case response time analysis. Now, let us try to understand what is response time. I think we already have defined this, like you have a task that has been released, and then that does not mean that, well, the task will be executed immediately, right, and the task will eventually get executed, it may get preempted, and this can keep on happening, right. And eventually when the task finishes, so you have this interval when the task started and when the task finished, right, and when the task was released and when the task is finished, and this is what we call as the response time of the task. So, typically for a periodic task, we will be representing them using this kind of a 3 tuple for task T I. The tuple will contain period P I, deadline D I, and the execution time E I, right. Now, the tasks can have a unique fixed priority. Okay. You can have a deadline monotonic scheme or a rate monotonic scheme or any other scheme like that. All tasks are preemptive, and for each task we are assuming that the deadline is less than or equal to the period. So, there is a catch here. So, if we do not mention the deadline, you can assume that deadline is equal to period, but we can mention the deadline. Of course, the deadline has to be less than or equal to the period, in that case. Okay. So, when I am talking about fixed priority algorithms, the priority may be decided by the rate or the period, or the priority may be decided by the deadline. That is another variant. Now, suppose we want to figure out what is the response time of the task. Response time we have just defined, right. Now, why do I want to figure out what is the response time? Because for a real time task we require that the response time must be less than the deadline. So, when a task's period starts, we know that well, unless there is any offset or something specified, that is the point where that task instance has been injected into the system, or the task instance has arrived into the system, and from that point up to the point where the task finish, this is what we call the response time. And in a hard real time system, we want the task to finish before its deadline, right. So, this is a constant which is important for each task T I R I, the response time must be less than or equal to D I. So, we will like to know how to compute this quantity R I. Okay. Now, if you are given a fixed priority preemptive scheduling scheme for a given task set, the response time for the ith task is typically given by this kind of an equation. So, for the ith task R I is equal to the execution time E I plus this summation, and you are carrying out this summation over all tasks who have a higher priority than this ith task. Okay. So, for all those tasks, what you are doing is you are having that response time of I divided by this period. So, you see that for all tasks we have assumed this tuple, right. So, P is the period, right. So, for all those high priority tasks, for the corresponding, let us say you have picked up some j value, what is the period of that task, you divide it, right, and then you multiply this by the execution time. So, let us understand philosophically what is happening. So, I am saying that well, right now let us say I have an approximate value that well, the response time of this ith task is this. So, that is one interval, right. So, inside this interval, how many instances of the jth task can occur? So, that can be figured out by dividing this R I by this by the period of that jth task P j, right, and this is your R I, this interval is this is R I. Okay. Now, if I get that many task instances. Now, as I have said, I have taken the summation only over tasks which have got higher priority than the ith task. So, it is expected that all those instances of the jth task will come and they will preempt the ith task, and they will consume the CPU for each instance for this E j amount of time, right. So, inside this response time, I will be interrupted this R I by P j number of times, and each interruption will be of an interval of size E j, right. So, those times my task maybe it was trying to execute, T I was trying to execute, but that high priority task J O is coming, it is interrupting me and it is consuming the CPU. So, I am just figuring out how much interference I have from this jth task. Okay. I think now it will be a bit clear, and similarly I can figure out the interference on me the ith task caused by all such other j values of tasks which are of higher priority than me, because all of them are going to interrupt me. All of them are going to interrupt me for their execution time, and that phenomenon is going to happen that many times that they come inside this response time. Okay. Now, the question is well, this response time value is not known, right. So, if you see this is like a recurrence equation. What we are doing is we are getting an estimate and we are refining that estimate by applying this equation. Okay. So, that is why let us say my nth estimate is given by R I n, I apply this equation to get the n plus 1th estimate. Okay. So, initially we will assume that this value is 0. So, initially I will only have E I as my initial estimate of my response time, and then we will compute this recurrence and we will keep on computing it until and unless I get 2 consecutive iterations of this recurrence giving me the same value. So, that means this computation has reached a fixed point and that is my response time value. Now, notice this symbol here. So, that is like the ceiling symbol, because this ratio may be fractional. In case of fractional, I will just try to round it up to the next whole number, and that is why we take the ceiling here. So, let us take a simple example here of response time analysis. So, let us say I have a CPU, an electronic control unit in a vehicle, which has got some tasks, this T1, T2 and T3. So, these are not messages, these are, let us say, periodic real time tasks. And they have the periods and deadlines and execution times as mentioned. Let there be, tasks have different types. One is a security monitoring task, that means it will execute once every 30 millisecond, and it will try to finish its execution inside 15 millisecond, and each time it executes, it will consume 5 millisecond of the CPU, and it is monitoring what activities are going on, whether some values or its monitoring are wrong, and then it will raise an alarm, something like that. It has got a priority 2, and then there is a sensing task which is also running periodically. There is a control task which is running periodically, and the sensing task has the highest priority. Let us just consider this as a very symbolic example. Okay. So, these are fixed priority scheduling we are considering. So, note that because that their priorities are with respect to the periods here. Now, note that the control task has the same deadline as its periodicity, this one. Okay. Now, we need to check whether for this control task the deadline is greater than or equal to the response time value. So, if you just look into this calculation, so just like we said, the initial estimate is 0. Now, you apply this equation once. Okay. So, we are computing it for the control task. Okay. So, that means this has a priority 3. So, it can be interrupted by which tasks? It can be interrupted by this sensing task and the security task, right. So, if you see here, so our target is to compute for this control task, right. But let us start with this one first. We are trying to see for this security task. Okay. So, R1. Now, R1 has priority 2. So, the only one of higher priority than that is T2. Okay. So, it can be interfered with by this T2. So, when I factor in, I will just factor in the execution time. Let us say this is the response time estimate. I will of R1. I will divide it by the period of T2, and I will multiply this number of instances with execution of T2, that is E2, right. So, initially this is 0. So, all I get is E1, that is 5, and then I will refine it to 13, and then I will soon see that well it is stabilizing at 13, not changing, right. So, for T1 it is getting satisfied. Now, let us see for so this is for T1. Now, let us see for the sensing task. This is the highest priority. So, there is absolutely no interference. This kind of ceiling based terms will never come. So, it is all about the execution time only. So, it is just response time is exactly equal to its execution time. Whenever it comes, it gets the CPU. This is fixed priority scheduling. So, there is no issue at all. Period, deadline is 12. Sorry, here this should be 12, not 20. Right, and 8 is always this the execution time that which is equal to the response time is always less than the deadline here, no problem at all with that. Now, what about T3, right, with period equal to deadline equal to 30, and we want the response time to be less than that. So, let us see. So, for T3, if we just try to compute that value. So, the 0th estimate is of course, we can I mean we can either write this or we can just do the other, that means interference of the second task interference of the first task, but of course, I have taken this to be 0. So, this is coming just is E3 right, or you can simply take R3 1 as E3, you can just start writing from there. So, that is not a problem. So, this is actually 12, and then what about the second the refining the estimate, you can just write the equation. So, this is 8, this will come as let us see. So, this is 5, and similarly you can get this as 8 and you will get this as 25. So, you can now start with 25. So, again you have 12, so these are ceiling relations. So, you get 2 and here you get a 5. So, that is 33. Okay. And if you keep on doing this, you can go to the fourth estimate, which should again be 12 plus, you can see this is 33 right. So, the previous estimate is 33. If you keep on doing this, so this is again going to give you, I mean it is rounded up to the next whole number. So, that is 2 and 16. So, this is again rounded up to the next number, right. So, you get 38, and then you can just check that if you get the fifth estimate, I am just trying to show you that this really is going to terminate. So, you see it has, because again you are getting the same values, because this is 10 and this 38, which is equal to your previous estimate. So, you can now stop. So, what you get now is the response time for task 3, and that comes to be 38, which if you compare with the deadline is kind of is going to overshoot the deadline, right. So, that is a bad thing. So, if we are doing this kind of rate monotonic scheduling and if you do the response time analysis, this is clearly violating the deadline. So, that's it. That's how we go about doing processor scheduling and I mean computing response time for task sets with fixed priority. So, with this we will end today's lecture. Thank you for your attention.